Welcome to Geometry Lesson 9.6, Surface Areas and Volumes of Spheres. Here's a slide with 3 new formulas, and we've actually done these formulas in the past. You've also done them in algebra, so they should be somewhat familiar. So, just to review, a sphere is a set of all points in space that are a given distance from the sphere's center, and that a radius is any segment from the center to the point on the sphere. So if you look at the inside of this sphere, there's a point, and it's the set of all points from that center. So from the center of this sphere to the outside of the sphere is the actual set of the sphere, and it actually has a radius and a diameter and all the same things that circles have, and we'll get into that. So a chord of a sphere is a segment with endpoints on the sphere. So a chord will be, if I can get my cursor to appear, there it is. A chord would look like this. The diameter of a sphere would be on the inside of the sphere and go all the way across. The tangent of a sphere contains exactly 1 point, so a tangent might run on the outside of the sphere and it would have a point of tangency. Secant of a sphere contains more than 1 point of the sphere. The chords and secants will look similar. A secant line, this would be when you have a line going, let's try that again, a line going through the sphere. We can also use this line at the bottom of this plane here to show you what a secant line would be. And the intersection of a sphere and a secant plane is a circle. So the intersection of a sphere and a secant plane is a circle. So we've already talked about this. These cutouts or cross sections are actually circles, and if we try to solve for them, we use the area of a circle to solve. Now here's some new information. If you draw a circle around a sphere, it's called a great circle if it's in the center of the sphere. And it's essentially formed by a plane passing through the sphere's center. All great circles of a sphere are congruent, so no matter where I drew this on the sphere, they would be congruent. And the circumference of a sphere is defined as a great circle. So if you need to find the circumference of a sphere, you'll actually be finding this imaginary line on the sphere. If you have 2 great circles that are perpendicular to each other, they actually separate a sphere into 4 sections. Think of an orange where you cut it into quarters. Each one of these sections is called a lune. Not sure why. It has something to do with its link to the lunar surface and the moon. If the planes that generate the great circles are perpendicular, the surface of each lune, so each one of these quarters, is equal to the area of a great circle. So the area of the great circle in the middle of the exact middle of the sphere would be equal to one of those lunes. And from that fact, we derive the formula for the surface area of a sphere. So if the area of a sphere's great circle is pi r squared, the area of a lune is pi r squared, and the surface area of a sphere is 4 of those, or 4 pi r squared. So we actually have a theorem for that. And we have theorem 9.6.1. The surface area of a sphere is the product of 4 pi and the surface area of the radius. So to solve this equation, you would need just your length of the radius. If you have a diameter, you'll cut the diameter in half and then use this formula. Example 1. The moon can be modeled as a sphere with a radius of 1,738 kilometers. Find approximations for the circumference and the surface area of the moon. So the circumference would be 2 pi r. We know that the radius is 1,738 kilometers, so we insert that information into our formula. 2 times 1738 is 3476 pi kilometers, which is approximately 10,920 kilometers. And it asked us to find approximations. That's why we're going the next step. Surface area, we'll take our answer for the radius here, which is 1738, and our formula is 4 pi r squared. So if you square 1738 and multiply by 4, you'll end up with 12,082,576 pi kilometers squared, which is approximately 37,958,532 kilometers squared. That brings us to our next theorem, which will be the volume of the sphere. So theorem 9.6.2, the volume of a sphere is the product of 4/3 pi and the cube of the radius. So I'm not going to derive this formula for you, but this 4/3 has to do with those lunes also. So 4/3 pi, and because we're solving for volume, we'll now have the radius cubed. Let's look at one more definition, then we'll have an example. Sometimes in these figures, you'll have some questions where they might put a cylinder, a small cylinder inside of a large cylinder. When they do that, you actually end up with an area in between them, and they call that area the annular ring. So you'll have a smaller cylinder, and in this case we'll say the smaller cylinder has a radius of small r, and you'll have the larger cylinder who has a radius from the center of the circle to point B, which is capital R. So the formula to solve this easily, and this is intuitive, you'll find the area of one and subtract it from the area of the other. So the area of an annulus, or an annular ring, is the area of the large circle minus the area of the small circle. And the reason I wanted to show this to you is so you can take a look at this notation. Sometimes they'll have a capital R and a small r. Sometimes you'll have an R and a T, or R and S, something like that. All you have to do is substitute that into your formula, and just remember you're using the radius from the large circle, subtracting the radius from the small circle. Example 2. Find the volume of a sphere with a diameter of 10 inches. So we have a radius here, and that's what we need for our formula. So let's take this diameter and solve for that radius. The radius is the diameter divided by 2, which is 10 divided by 2, which is 5 inches. So the radius equals 5. We substitute that 5 into our formula, which was 4/3 pi radius cubed. 5 times 5 is 25. 25 times 5 is 125. And 125 times 4 divided by 3, or 125 times 4 is 500. We still have our pi. We leave this as divided by 3, and this is approximately 523.6 inches cubed. Example 3. A ball has a circumference of 22 feet. So this is the line, the great circle around the sphere. Find the ball's radius and the number of cubic feet of air it can hold. So we're looking to find the volume. So circumference is 2 pi r. They told us it's 22 feet. So 22 equals 2 pi r. If we divide both sides by 2 pi, r will equal 11 divided by pi feet, which is approximately 3.5 feet. We can now substitute into our volume formula. And I recommend you use the pi form of the previous answer because you can see that your pi's are related to each other here. So we have 4 divided by 3 pi times 11 divided by pi cubed. And if you go ahead and use your calculator and multiply 11 times 11 times 11 times 4, you end up with 5324. It'll be pi squared, and that'll be feet cubed, which is 179.8 feet cubed. If you have trouble with the steps in between here, just contact me and I'll walk you through them. So our homework. The homework should be fairly easy. Most of the problems follow the formulas. So numbers 1 through 2, 5 through 6, 9, 11, 14 through 15, 30, 31, and numbers 49 and 50. So number 30, you're going to solve for the volume of a cylinder and 1/2 of a sphere. So this is a situation where you'll use your volume addition postulate and solve for two separate figures and then add them together. Number 31 is similar. It's solve for a volume of a cone and 1/2 of a sphere. Number 49 is a construction, and this is for a dodecagon, which is a 12-sided figure, and we need more practice on that. Remember, a dodecagon is a hexagon that has its sides doubled. So in lesson 8.6 constructions, I sent a link to a video to actually do this dodecagon if you can't remember how. Number 50, if you got this wrong on your Chapter 8 exam, please take a look at page 382, construction number 14, and you can also go back to the video and check out how to take that angle and place it inside of a circle. So if you need any assistance, please be sure to contact me. To let you know, there is a change in your lesson plan. I will be emailing those changes right after I email the link to this video.